Okay, good morning again, and welcome to this next class. I'll share my slides and then I'll start talking about the subject. Somehow I need to do it in 2 steps because full screen is not shared without that. And okay, so now you have on your screen the slides. And one of you confirm that you can see my slides and you can see them moving?
Yes.
Okay. Okay, thank you. So as in continuation of our last class, we were describing the representation of an agent program, particularly the representation of the environment in which an agent operates. So for instance, the vacuum cleaner or an air conditioner, you can think of it as made up of atomic states. So when atomic states is described, you say that my entire world in state 1 or state 2, you can have any number of states. And if the environment for the agent is described in terms of a state in these plane states, which may be a finite number of states, and then you say as the system evolves or system and the agent starts operating and the AI device starts working, then each step of the operation can be thought of like movement of or the transition of the environment from one state to the other. So this can be any real physical environment, or this can be an abstract construct, or it can be a sequential environment. So for instance, an example of an atomic representation of the environment or the system agent program is hidden Markovian model. Does any one of you know what is hidden Markovian model? Have you ever heard of this or read about it? Just quickly describing conceptually what is a hidden Markovian model. Anyone? Have you studied this anywhere? Say no if you're not studied. I mean, you can just raise your hands if you have studied. So you can just quickly discuss this, and this may have implications for designing your algorithm or agent program based on HMM. So nobody has heard about it. So hidden Markovian model is a representation of a sequential environment in which there is, we think of to a visible state, an outside state, and a hidden state. And we think that the visible state that we have is resulting from a sequence of events that is happening in a hidden world. For example, a casino. So in the casino, suppose somebody is playing a game of casino and then he's winning or losing. Suppose the only 2 binary states are possible. And in the hidden backend model, there may be numbers like 1, 2, 3, and a sequence of numbers. And based on a certain number, a victory will be declared or a loss will be declared. So the numbers that are being played at the back end are basically the hidden sequence of numbers. So sometimes a question in HMM is asked whether can we tell by just looking at a sequence of numbers, can we tell that the dice which is being used now is the same dice that was used earlier or it has changed? So that can be trained by looking at the sequence of numbers that one dice can produce, and another dice will produce different sequence of numbers. And the model is described in terms of the state. Each number can be thought of as state. Suppose only 6 numbers are possible, 1, 2, 3, 4, 5, 6. Then if you randomly throw these dices, you will find number 1 comes, then maybe 3 comes, then 6 comes. So this sequence of numbers that you have is a kind of a hidden state. And then if the dice, whether it is a dice A or dice B, let us say this is our visible state. So if I look at these numbers, can I tell that the sequence of numbers that I'm now receiving is a likely sequence from dice 1 or from dice 2? So in a summary, that there is some hidden sequence of events that is going on. These numbers may not be visible to us, or maybe visible. Some states may be visible to us. So the sequence, if we describe the entire environment in terms of just states, we call it an atomic representation of our environment. So A to B to C, or there may be any sequence. So when we were at this, in some other representations, we describe our environment as a factor, as a set of features. Like you may be familiar with machine learning models. In machine learning models, you give a data matrix, typical, say, machine learning model, say, neural multiple layer perceptron, MLP, or a Bayesian model, or a naive Bayesian classifier, where you have you sort of place each instance of your data uh, as made up of certain features. These features or attributes. So these features and attributes are basically the factors of your state. So you may not label individual states in A, B, C, and you are not describing them going from A to B to C, etc. But you are representing them numerically, and you are saying that my current state or my current object, if it is not sequential, is made up of certain factors, and these factors or these attributes have certain values at a given time. So these factors are not changing over time. The values associated to these factors or attributes is changing, and that would determine, suppose I want to predict the next vector in my time series, then I will try to develop a machine learning model, or maybe it may be a recurrent network, or it may be any time series based modeling, and I can try to predict what will be the outcome in the next step. But in terms of representation, that if I represent my entire environment as made up of states, where I do not look as the detailed structure of these states, then it is called the atomic state, atomic representation. When I describe each of my current state of my environment as made up of multiple features or attributes, and we associate some numerical or categorical values to these attributes, we say that I have a factored representation of the world state. In some cases, even factored representation may not be sufficient. Say in the machine learning model, if you have 100 attributes of each instance, which is evolving over time, then even these instances, for most practical purposes of machine learning, are not treated as interacting with each other. And therefore, some of the relationships that may exist between these features may be not truly modeled from from models which do not capture relationships between them, or where the world is not represented as a set of interactions. So for that, we have a structured representation of our environment. In the structured representation of our environment, you not only have the features or attributes similar to the factored representation, but also have described what is the relationship between them. So that is called a structured relationship. So you may have first order logic, first order probability models, these natural language models. Like for instance, if you just have the attribute representation of a natural language, I have a sentence and I have, say, let us say, subject, verb, object. And then if you just treat them as subject, verb, object, or for semantic web, when you also talk there about the predicate and the document formatting systems. So there also you may have just a factored representation where the actual sequence, which word comes after which word, is not considered. But in the structured representation, then the relationships will also be important, so that if A is acting on B or B is acting on A can be distinguished, which cannot be distinguished in the factored representation. So in the structured relationship, or which is more like a network or like a graph of the world attributes of which our world environment is composed of, is the structured representation. So these representations are important because if we are trying to solve an agent program, if we are trying to determine the action from an agent program, I need to first represent my world, my environment on which this agent program is acting, on which it is determining the actions. So we'll come to these representations. So, and then combining all this we have discussed in summary, we will now discuss how actually a rational agent will decide its action. So we defined rational agent could possibly just do table-based representation or reflexes. So in those reflexes and the table-based representation, we did not consider how actually an action is selected. What we considered there was that suppose we have a mapping that if this is my state, environmental state, if this is my percept or this is my percept sequence, this should be the action. So their kind of mapping is provided. But now how this mapping is developed, with what purpose, that we'll look at. And for that, there are methods, algorithms that we will look into. So we restate our problem that we have a percept or percept sequence, and you have an agent program. Then agent program will consider what is the goal of the agent, what does it want to achieve. And if this is goal, if this goal is not completely achieved, how do I measure what is the performance of my agent program? And then based on that, if I take this action, my performance will improve. If I take another action, my performance will drop. So based on that, this agent action will be decided, and then the feedback will go back to the percept. It becomes a part of percept. So and this particular part of the slide, which says that the basis of the action decision agent's action will be to ask this question: what will maximize performance measure? Such an action should be selected which will maximize my performance measure. So now we discussed in the last class, there are some reflex-based agents where only the current percept is considered and the next action is decided. But then we may also have described in terms of problem-solving agents and planning agents. So there are two types of agents that I'm talking about here. One is called the problem solving. We define this is my problem. Suppose this is my chess game. And here I know the result of the chess is I win it. And then there are certain conditions in which the victory is decided. So that means that can be thought of like a problem to solve, or there is a jigsaw puzzle. Or so the solution, whatever can be achieved, the solution which is defined by the game designer, that is to be reached. And now if the current representation of my jigsaw, which is not yet completed, in that jigsaw, I can describe how I go from the current state of my jigsaw or any puzzle or a game. So what is the current state where my players are located? How should these players move? How should these states change from now to next level? How can I go from this state to the next state and next state and next state so that I can reach my goal state in the fastest possible manner? So this is how we'll define our problems. So as is written in the first point on this slide, that problem solving agents use atomic representations of their environment. So for example, if you have a chessboard, so atomic representation would mean here, can somebody do a atomic and factored representation of a chessboard? Just do it for me. And I've just defined broadly what is an atomic representation and what is a factored representation. So can any one of you pick up from here and tell me what will be atomic representation of the chessboard, and what will be the chessboard state, and what will be a factored representation? Anyone, just think about it so that I understand you have grasped the idea of atomic representation well. Okay, let me ask it differently, which will be easier for you to answer. What will be the dimensionality of my atomic state representation of a chessboard state? So when I'm saying chessboard state, I'm saying where is each pawn and each block is placed, and what is the current configuration of my chessboard? What is the dimensionality of how many states I have to define if I have to say represent my chessboard in atomic representation?
And
Rahul, your voice is not very clearly audible. Maybe you have to move around.
which column, which sir, which row, which like on or what, and which color? which color, which row, which column, which character.
Yeah. So there are these three coordinates.
4.
And how many? So 3 coordinates. That one of them is the one coordinate is describing the XY coordinates of the positions, and the third will describe the name of the second may describe the color, and third may describe the actual
Character.
Yeah. So what are, if I have to define the states, how many states will now be possible? You can give me a rough number, if not exact.
Like total number of configurations of XY into means total possibilities of color into total possibilities of font, like means
Yes.
whatever character.
So roughly how much it becomes? Let us say I'm just putting one color. I'm ignoring the second color. So how many representations are possible? Anyone?
64 into 6.
64. Why 6?
Means like there is a pawn, knight, a rookie, and pawn, knight, rookie, and some 3 queen, king, and one more, I guess.
So you're not you're not distinguishing between different pawns and different rookies.
Yeah.
Okay.
Means they will be different actually.
Okay, for just estimating the order of magnitude, let us keep simplifying. Let us say yes, okay. I don't distinguish between different pawns. Then roughly what is the number of states possible? It is huge, isn't it?
Yeah.
So each of these 64 positions can be occupied by any of these pawns and the king and the queen, etc. So the number of atomic states in this is quite large, a combinatorial equation. I can't quickly get the number, but just to give you an idea about how complex it is, because all possible combinations, when I say one state, so what is this one state? One state is actually composed of the each position of each particular block in every block where it is. Out of the 64 positions it can take. So you can think of if all of them were the same pawns, just let us say, I'm just trying to place 8 pawns in 64 positions. So how many combinations are possible? 64 positions available and 8 pawns to be placed in them. So how many different states will be possible just from 8 pawns?
64 factorial by 56 factorial.
Is it factorial? Or combinatorial will be C? 64 C8.
Yeah, both. Yeah, both ways. Like yeah.
64 C8. So no, it is not. It is more than what you are saying. 64 factorial is will just give the position of how many? One of them. Not one of them. How will you do 64 factorial? How will you do solve 64? Oh, you already divided it. 64 factorial divided by 64 minus 8 factorial into 8 factorial. That's the definition of the combinations. So 64 C8 combinations are possible for the states. So these many states. And if one of these states is your goal state, and your current state is not the goal state, and you want to move around from the current state to the goal state, I'm just simplifying the problem. Let us say I have just 8 pawns, and out of all the possible representations, all the possible states, one particular state is your goal. And some moves are allowed that you can go from, you can move one pawn like this, or you can move the second pawn like this. Suppose these moves are allowed, and you have to move to the goal state from the current state in the fastest possible manner. So there you have to decide, I move this pawn. So as soon as you move one pawn, you are in a new state. Then you move the second pawn, you are again in a new state. So problem solving approach works like this. So problem solving approach will, the method will be that you define an initial state, the current state, which may be random. And then you define a goal state, which is a single state. And then you want to go from the current state to the goal state in the fewest number of moves. So that is how I will describe it in more abstraction, but broadly speaking, and a problem solving agent, when it is trying to solve a problem, it will have to define a goal state, and it will first represent the world, the environment in which it operates as an atomic representation. So when I said that the position of each pawn has been defined, so I am now operating in an atomic representation of my chessboard. Atomic representation of chessboard is not represented as it is visible on the chess, but it is like an entire goal state. So every possible state here. So this is one way. If I were to define this as a factor representation, what will be my dimensionality? Again, let us simplify the problem to 8 pawns being placed on 8 by 8 chessboard. So if I were to represent this now as a to do a factor representation of different states, how will I do them? In a factored representation, I can simply draw 8 rows if I have 8 pawns, and then XY coordinates on the column. So I can simply say about where it is present in that location, I'll write 1. When it is not present in that location, I'll write 0. So each pawn position can be represented as 2 factors, X and Y positions. So the dimensionality of this representation is much smaller than the atomic state representation and now you can plan. But the problem is that in this representation, I do not know from the current state what is the nearest state. I have to find a way how to move around in this factored representation space. Moving around in the space which is described as atomic representation is easy, and I can think of my move from the current state to the goal state. I can think of like I'm in a graph where each node of the graph is representing one state. And I know that from the current state, I can only go to certain states. I cannot go directly to other states. So that will define my actions, possible actions. I'll come to this. But you broadly understand what I mean by atomic representation and how the atomic representations are critical for the problem solving agents. So the problem solving agent may work in single or multi-agent environment. We can talk about this later, but let us say again, another example here. If I have to solve problem in fully observable, deterministic known environments. So if I have to navigate, suppose I'm JNU and I want to go from here to Delhi University, or somebody is trying to come from Delhi University, some location to JNU. And then what are the different states, atomic representation states for a driver available to you? Can you now associate to this problem your states, atomic representation states, and how to navigate around them? Anyone?
Every possible path. Every possible path will be.
Path is not the state. That is what I want to emphasize here. Path is not the state. Path is actually you have to optimize your path. You have to find the best path.
Using GPS, we will find our state.
No.
It will be
So you are currently located somewhere. So this is your initial state. And now you have a goal state. Suppose you are in some location in Delhi University, that is your current state. And your goal state is to reach JNU. So the location where you are is your first element of your state. So every traffic signal may be thought of as like a state. That is your location. But you may also incorporate additional factors of the state into your state, which may be whether there is a traffic jam, whether the traffic signal is red or yellow, or you can have additional information there. But every time you are somewhere, that describes your current state. And wherever you are, from this state, you cannot directly jump to the final state. You have to find a path to reach the final state. So your problem solving formulation will be your look. If I ignore all other factors, every traffic signal can be considered of your can be thought of your state. So you go from one traffic signal to the other traffic signal. So you have gone from one state to the other state. And if I ignore all the factors and I say that every traffic signal, you have to decide whether you will go to right or whether you go to left. This decision to go to the right, to the left, or to straight, or if there are 5 roads at some location, these are the actions. So this your agent program at every traffic signal has to define your action. In a more elaborate agent program, you may have to take additional decisions about what should be your speed, whether to apply brakes, whether to move the steering. Those may be details, but in the very simplistic form, your action, your states are your locations at every traffic signal, and your actions are your decision to move right, left, straight, whatever are the options available at every traffic signal. So these are the actions available to you. Out of those actions which are available to you, your agent program will decide this action has to be taken. And this will be done using some model, and you have to, again, in order to take the best route, now you have to define what is best route. I'll come to that. But this is another illustration of how simple agent programs should operate and what try to do. If it is fully observable, that means there is one possibility that right when you want to decide the best route from the beginning, there are 2 possibilities that your environment is fully visible. That is, right in Delhi University, you know what are the different possible traffic signals that come on the way. If you change the path, these are the traffic signals. Suppose you have the map and you start finding out your route on the map, and you know the location of every traffic signal. So in this scenario, your environment is fully observable. But you may be in some location where you do not fully know about the entire map of the place. You have some idea, you have some measure whether you are going closer to the destination or not. So in that scenario, you have to operate differently, which is not fully observable, partially observable. And it is maybe deterministic. You may know if I take the right signal, what will happen? If I take the left turn, what will happen? So this may be deterministic. What will be the consequence of your actions? If you can determine beforehand, they are deterministic, and they may be known environments. So I'll take more examples and specific cases and specific methods to solve these problems. So the non-deterministic and failure-prone models need monitoring. So all the time you have to keep checking whether I'm getting closer to the destination or not. But if you're one important point that in the previous slide that is on the bottom I have written is, if the model is correct, and if you know the environment completely, then once the agent has found a solution, you found the path and all the factors that you have already considered, and you found that I have to go from action 1 to action 2 to action 3, so that my state becomes a state 1, state 2, state 3. So you select the number of states that you will navigate through, and you know this is my final destination. So right in the beginning, you can work out the best route to reach your destination. If now you have worked out the best route of your destination, now right in the beginning, you do not have to monitor where you are right now. You can just continue to follow that route. So this is what will happen in case your environment is fully observable, deterministic, and a solution, best solution can be found at the outset. But if your agent is operating in a more complex environment, where you also look into the traffic conditions, where you also look whether there's a traffic jam, whether the traffic, if the signal is long or short, then you have to constantly monitor your environment, and you need to take a feedback, and based on the current inputs from the environment, current percepts that you are receiving from the environment, you will have to find the best solution at that instant of time. That means the optimum path or optimum solution cannot be computed right in the beginning. It will be computed only as the action sequences proceed. So in the non-deterministic or failure-prone model, you need to do a constant monitoring and while you execute your actions. And if there is no chance of model failure, you may be in an environment when the model, you have created a model. The model here means how will you decide your agent action. So if you have created a model, this is how I will take decisions, and the environment is completely deterministic. So then agent can simply execute the sequence of actions once the model has given a solution. So it may have given solution right in the beginning. It may give a solution at every stage or whatever. So this is called the open loop system, where the solution is guaranteed based on your all the actions can be evaluated and the best solution can be found in the beginning. In a non-deterministic environment, when we do not know things beforehand, what will happen if you do this action, and or when the certain action relationship with the environment is probabilistic in nature, it is not 100% guaranteed. What will result? What will happen if you take the right turn? Will you be stuck up in the traffic jam? If you go straight, so will it be faster to go? So these kind of sometimes non-deterministic or partially observable systems will have will are considered to be kind of closed loop agents, where they have to operate and they have to constantly monitor themselves. So we'll mostly discuss in the subsequent classes the open loop systems and some closed loop systems also. So again, now returning to what I described in a formal manner. So in order to solve the problem, what are the steps required? You define a state space, which is the atomic state. I say that, like I was saying, navigating. So I define my atomic state to be my location at every traffic signal, where I have to take a decision to turn right or left. I'm not taking any other decisions. I'm just going from one state to the other. Or in a game, my states refer to the current complete configuration of players in the game board, whatever game I'm playing. So that is the entire description describes a complete single state. And then from the current single state, you will define what are the possible states that you can go to. You may not be able to go to all states from the current state directly. So all the states which are directly accessible in the current state will determine your action. And yet then you will choose, okay, action to go to this state. That will be your action. So first step is to define a state space where you completely describe, like in the case of 64 options for 8 pawns, 64 C states. So that will be the first stage. We define this numbers of states that are available to you. These are called state space. You define the initial state of the agent, where it starts. It may be a randomly started position, or it may be a well-defined initial state. You define a goal state. What do you want to do? Like in the game, I said there may be one state where I say that, let us say all the pawns are in the corners. This is what you want to achieve. Then if I want to achieve this, and there are, we already have defined my current state. So how to go to the goal state from the initial state, that is what has to be done. And actions available to the agent. I already mentioned action available to the agent means some of the actions are allowed. If my entire state space is composed of n states, then every state I cannot be reached from every state I minus 1. So only some of them will be possible to be achieved. And then this will describe your complete agent now. You define a state space, you define the initial state, you define the goal state, and you define what are the actions available to the agent at a given state time. Now you can say, given a state S, this is a formal description, given a state S, action returns a finite set of actions that can be executed in S, which is a state, current state S. Vector S is the state space. We say that each of these action is applicable in S. So allowed actions, we say they are applicable in S. So again, example actions, I already mentioned. So we can describe, you write usually in this language that action at Delhi University, the current location, I can take this action to NM road. So this is the road I want to take. And then I can take my next action maybe to Kabir Basti Marg. So these may be my different actions, and these are the two possible actions out of which one action has to be selected. If I take this action, maybe I reach faster. If I take this action, maybe I reach faster. Now, the whole exercise of finding the best solution will be how do I reach the goal state in the fastest possible manner. It may look like initially I'm going closer to my goal state, but it may happen that in the long run, that route may be slower. So if I see that, okay, I can go to the right and I can go to the left, both ways will lead to the destination, then and also straight. So out of the three, I know that two of these routes will take me to the destination, and it might look like that the right side of the road is free. And then at that time, if the world is partially visible to me, I will be tempted to take the right route. But then later on, I might find that there's a traffic jam and this route, now I have no way to go back. So this may happen that if the world is partially visible to me, my action sequence may be correct, not incorrectly selected, and it may not select the best solution to the goal state. Okay, so now we have to also describe the transition model. The transition model will tell me that if I do a particular action, how the environment around me will change. So that I have to define the result. That means I'm starting with the action. I take my current action is suppose my current location is DU. This is my current state. And after I have taken the action, my new state may be JNU or maybe another location. So I have to define a transition at every location. If I take this action, where will I be? What will be my new state? Also, I have to describe for the purpose of whether I'm doing well or not, or whether a particular path will be a good path or not. For that, every action that I take, I must assign a cost to it so that I can say, if maybe I achieve something in 10 steps, maybe from Delhi University to JNU, I have to just cross test 10 traffic signals. And there is another route where I require 20 traffic signals. So should I choose the one which has 10 traffic signals? Is it a good idea?
We are assuming the distribution of traffic signals is uniform along the route.
You can't assume that, right?
Yeah.
So that is what is important here. You picked up the right thing. So we cannot decide just based on the actions, list of actions, whether a particular route is better or not. For that purpose, what you are saying, distance between the traffic signals is what is equivalent of what is called action cost. That is, if I go there, this traffic signal has a greater cost, this traffic signal has less cost. So it may be distance or it may be other conditions, whatever it is. Maybe there's a toll road there. So action cost will consider every factor that has to play a role in deciding the action, which will ultimately determine my performance measure. So every action in a sequence of actions returned by the model involves a cost. So you define the distance in the driving mode. You just mentioned the distance, or it could be as I said, toll, or it can be any other factor. It can be time taken instead of the distance, because the traffic conditions will determine the time. So anything, so this will be basically a model of your action cost. So this is also what you required for every action. What is the action cost? Formally describing action cost of taking an action A, when initial state is S and final state is D, the cost may be, this may be a uniform cost model, as Aditya just said, that if I assume that all my traffic signals are equivalent and distance between every traffic signal to this current next signal is equal, then all action costs will be equal. So you can define the simplistic action cost model, which can be considered to be unit cost model. So unit cost model means that one action, one cost is one. So, but in general, that is probably never applicable. In real situations, you have to work out an action cost model, which can actually compute the cost for you. So action to cost now can be C, which is a function of S, function of A, and function of B. So S, the state, the initial or current state, A, the action, and D is the final state, so destination. So state, action, destination, it may be a driving time or anything. So this will determine that if I know the current three values, what is the cost of this. So again, state is space graph. If you now represent this as a graph, I'm gradually coming to describing states, atomic states, and now I say that from one state you can go to another state. So you can think of your entire exercise is a finding of your path to be made up of nodes on a graph. So what you can do now is, in search of based problem solving, agent can be described by a state space and can be represented as a graph. So a state space can be represented as a graph. That is, every traffic signal that I'm crossing, or every state on the chessboard or a game board, every current configuration, you can think of one node of a graph. And it is now obvious. How will you define actions on this graph?
the transition from one node to another, where the transition would have somewhat weights that we have in graph, and the weights would
Edges.
be action cost.
Edges on the graph.
Yeah, edges cost.
Edges on the graph will tell you what actions are possible. And so your entire problem solving can be reduced to a graph, where on this graph, every node is representing a possible state, and every edge is representing a possible transition from connected states. So it will be a directed graph or an undirected graph.
It should be directed.
It will be directed graph. It is possible that you may go from state 1 to state 2, but 2 to 1 is not possible. It may have both directions, or it may have one direction where the action is possible. So now state space graph represents a collection of all possible states, and also it annotates on this state space graph that this is your goal state, and how many nodes will be covered for the goal state. Now you already understand how I'm representing my actions, how am I representing states. So if I say now there is one initial state and one goal state, so how many nodes will be required to represent a goal state?
Could you elaborate on the question? I didn't get it.
Okay, so what I'm saying is that I now know that I already mentioned that my agent in this scenario is operating on atomic states, and the number of states that are accessible to my system agent is each of these is represented by a node. And now I'm saying that my goal of finding the best agent action is to go from my current state or initial state to the goal state in the shortest possible action cost. So now I'm asking, in this formulation, can you understand how many nodes are required to represent my goal state? How many nodes will be my goal states? It is kind of obvious, but instead of stating it, I'm just checking your comprehension of what is going on. Have you understood my question? Should I repeat it again?
Won't it depend on the problem of how many states we consider as the final state?
In some sense, you're right, but wouldn't it be confusing if I consider more than one nodes to be final state?
That could be the case, yeah. So there should be one node.
Yeah, so just one node out of the entire space graph will be your goal node or goal state. So one node will represent your goal state. And that is how the atomic states have to be defined. If your goal node is not defined as a single node, then that means your environment is not represented in an atomic manner. So if the environment is represented in the atomic manner, there will be just one state that refers to my goal state. And now, if there are more than one states which serve as the goal state, that may be a special case. For instance, in a game, you might say that either this will be a victory or this will be a victory. So in that case, maybe some modification to this definition will be required. But in broadly speaking, when I represent my state space as atomic state, one of these states will be a goal state. So think of this on a graph now. On the graph, your initial state is one node, and your goal state is also another node. So now you see the problem is become simpler in the sense that we can use the lot of graph theory mathematics to solve my problem now. If I have described my current state as I have this location, goal is the current state. This is my goal state. This is my initial state. And I know the action cost. That means in a unit cost, every edge is assigned a unit. but you may use a quantified cost also, but in a simpler model, let us say one. So now I know all the connections that are possible in the graph. And let us say if I want to find out the fastest way to reach my destination, in the lowest cost, that means the minimum number of edges to be covered. So I can apply all the methods of the graph theory here, and without bothering about where my ponds are, where my car is, etc., etc. I just need to first define this as a graph, and then I apply the graph theory here and find out the shortest path on a graph, right? So this formulation of a problem solving agent as a graph where the goal state can be reached in the shortest possible or path or with the minimum action cost, that formulation is the problem solving formulation of the agent. And that is, we'll come to the methods of solving these problems. So this is just the recapitulation. We have described the 6 components of the problem solving agent: state space, initial state, action state space. What are the possible actions I can do? So possible actions space may be global, turn right, left, or straight, or they may be specific to every node. There may be different actions. So this entire action state space at every node will form your action state space. Transition model. That is, if you turn right, what happens? Where do you reach? This is your transition model. Action cost, I already described. Goal state.
These in some sense are like finite automata.
Second. And
these the what you have described just now in the previous slide and until now, it seems like these problem-solving agents are just like a finite automata, where you have a number of states, an initial state, and they are transitioning from one state to another to reach a final state.
This is an interesting question. Let me get the answer from more of you, then I'll give you the answer. So does this model, the formulation of problem-solving agent as a graph, do you people think will work only on a finite graph? That is your question, Aditya, right?
No, I think I said that it looks like that it is a finite automata kind of computation.
I don't know about finite automata, but what do you mean? Can you describe what you mean? I'm not.
Yeah, in finite auto, it's one type of computation, the easiest type, where we have a sort of a set of states. We have one initial state, and we can have multiple finite states. So what happens is, from the initial state, given an input, which would be of strings, accordingly, it is deterministic. So from suppose we get the string that represents the letter A there. So we have a deterministic path that from, if there is A, we transition to this. And then vice versa, we transition. And at the end, if we reach the final state, the string is accepted. But if we don't, it isn't.
So it sounds similar, but I'm not an expert in that. So I don't think I can really give you a definitive answer to this. But one thing I must clarify here, that is that this formulation is not just valid for finite state space. This can also work for infinite state space. So for your automata computation, since that is not my area, so I will hold myself back on that. But this one I can, perhaps your comparison, what you're saying looks to me logical, and perhaps it's similar. Maybe I'll read about it after this class. But I must say here that this is not limited to finite state spaces. Can you tell me why I'm making this statement that this may work also on the infinite state spaces?
It should in some sense, because the way you have described the problem in the terms of a graph, we can, it seems that we can go on searching for greedy solutions in the yokai space, and then we can go forward. And we
actually, all you need is of course, there will be, as we describe the methods to traverse this graph, you will come across this, that you do not need to know all the nodes explicitly from the beginning. You only need to know the nodes that you have to traverse. And and these nodes can be dynamically generated as you are determining, you are building your path. So in that sense, because you have the flexibility of generating these nodes dynamically based on the method you are choosing to reach the goal state. So since dynamically you can generate any number of nodes, and even if your graph is infinite, you do not have to try all paths. You only have to make sure that the path that you have currently is the optimum in going to the next step. So in many scenarios, of course, ideally, if all the goal states are kind of independent and a path is possible through them, and your goal is to find the shortest path. We can easily convince ourselves that if we expand this graph further from here at this node, if we create more nodes here, my path will become longer. So then I can discard that part of the space which is beyond the finite one in which I'm looking. So two aspects matter here. One is that the nodes can be dynamically generated while I'm trying to look for the best path. This is one thing. Secondly, I do not have to traverse, or I do not have to try all combinations of the paths to find the best path. So the methods that we'll look in the subsequent classes is to find what is the best way to find the best path, and in which scenarios which method works and in which it doesn't work. So
you're saying in the infinite space we find intermediary paths.
no, infinite space may be such that you are going from goal state and the your current state to the goal state. You can prove that every other state out of these, every new state that will be created in the infinite space will be longer, because your goal is to find shortest path. And you suppose additional paths can be created in the space I'm not considering. If I can prove that the additional paths that you will create will all be longer than my current path, then I do not have to consider them. You get it?
Yes.
So if I have to just convince that these are my finite paths out of the infinite space, if any path that I create now, that means if I add another node, this will only become longer. So there's because I can figure out that where my nodes can be added. So if the nodes that are now possible to be added, so but that has to be now for such a formulation of infinite space, these infinite nodes are not just random. They are determined from some formulation, some mathematical expression. So for some mathematical numbers are solved, mathematical formulations are solved through graph-based approach. So if I do not have to search for all combinations, I'll perhaps take one example of this kind in my later slides. And but right at the outset, we can think of that all the graph does not have to be known a priori. You only need to know the graph that you actually will have to traverse to find the optimum path. Secondly, the goal of an intelligent agent is not always to find the best solution. The goal of intelligent agent is to find the usable best solution, which can be determined in a realistic amount of time. Because sometimes if you have the best solution can be found by brute force. And we just saw that if in a chessboard of 68 by 8 chessboard, there are so many combinations or atomic states possible. So formulation of all atomic states for a chess player is not feasible. So what a chess player does, chess player always has a method, an intelligent method to reach the goal in much fewer number of steps without having to consider all possible actions, without having to consider all possible states that he can come across. So he will take perhaps the reflex-based approach, that is just immediate approach, and will perhaps take, if I do this X to Y, Y to Z, if I go to step 1, 2, 3, 4, in five steps, what are the different possible combinations? So he does not have to try all possible combinations that if I play this player can play this 100 moves, then out of these 100 moves, I can try 100 different moves, then he can try 100 different moves. If a player has to do these exhaustive combinations, this will be enormously large. And even a computer cannot do in a realistic time. So therefore, the goal of the intelligent agent is to find an answer quickly, not just always to find the best answer. So what is the best way to find an answer quickly, and also an answer which is good enough? In some cases, we insist that our answer should be the best answer. In some cases, we insist that our answer should be determined fast enough. Not even if it is not the best, perhaps close to the best will also do. So this is the goal of an intelligent agent when it operates in realistic environment. And I skip this abstraction is just, I took this example. Okay. I think I stop here for today. We'll continue with the other topic about the abstraction of this. Any more questions or comments on what we discussed today? And I'm very happy you people are participating, and at least some of you. I encourage more of you to participate and give your comments. And be prepared that I may not know all the answers that your questions seek. We discuss some of them and perhaps discuss some of them after the class or later. But at least think about the questions and raise your questions and give different alternative opinions. I mean, even if certain formulation or certain rules of AI are available, they're not final. The subject is evolving and all subjects keep on evolving. So you keep on looking for fresh perspectives, the way things have not been seen by others. That would be very welcome to discuss here. All right then. Thank you for joining today. See you tomorrow at 2 o'clock.